Greetings to you. Yes, in my last class we had discussed about the atomic absorption spectrometry, instrumentation, automation and role of computer in the atomic absorption. Today we will continue our discussion regarding the technique of flame AAS. If you remember what I had told you earlier, that there are about 4 systems of atomic absorption spectrometry. One is flame atomic, another is graphite atomic absorption, another is hydride generation, another is cold vapor mercury. So, now we are going to discuss the technique of flame atomic absorption spectrometry. So, just like any other spectrometric technique, what you should do is you have to switch on the instrument and then prepare your standards. If you want to determine copper, you have to prepare the copper standards of 1 to 5 ppm, 1 ppm, 2 ppm, 3 ppm, 5 ppm, etc. and then make the insert the sample into the flame, record the absorbance. Okay. So, then you take it out, put your second sample 2 ppm, record the absorbance, 3 ppm record, then you plot all the absorbances versus concentration, that is your working curve. Then you put your unknown sample, record the absorbance and refer it to the calibration curve, that will tell you what is the concentration of the element. This is the general principle of all spectrometric techniques, including spectrophotometry, infrared or atomic absorption, flame emission, whatever it is. You have to prepare the standards and refer the standard curve versus standard curve corresponding to the concentration versus response and to your sample. So, flame atomic absorption is no exception. So, chemical analysis with flame atomic absorption is performed by introducing standard solutions of the analyte into the flame through the nebulizer into the spray chamber. The aerosol is carried into the flame where a number of processes take place. We have already discussed, but we will discuss it once again, and culminating in the production of the ground state atomic cloud. And these atoms absorb the radiation coming from the hollow cathode lamp, okay, coming from the hollow cathode lamp. Therefore, the intensity of the hollow cathode lamp decreases whenever there is absorption. So, the absorbance of the given sample corresponds to Beer-Lambert's law, that also we have derived earlier, and you have to plot the absorbance. The decrease in the absorbance is your concentration response. So, using the absorbance data, a calibration curve is constructed and the sample concentration is determined by referring to the calibration curve. Okay. So, the steps involved in atomic absorption are: number 1, switch on the instrument. Okay. Number 2, aspire your blank solution into the flame. Then note down the absorbance. This would be 100% transmittance. That means no absorbance, because there is no analyte element in your blank solution. Okay. Once you do this, aspire all the standards into the flame one by one and record the absorbance of each solution. Afterwards, plot absorbance versus concentration of the standard. This is the next step. Then what you will do, you aspire your sample into the flame and record the absorbance. Last step would be find out the concentration of the analyte by referring to the calibration curve. So, this completes the analysis of atomic absorption analysis of a metal ion basically. So, first you switch on the instrument, aspire your blank solution into the flame, note down the absorbance, this is 100% or 0 concentration, and then aspire all the standards and record the absorbance, and then followed by plot the absorbance versus concentration of the standard. Finally, you aspire your sample into the flame and record the absorbance, and from the absorbance you calculate the concentration by referring to the calibration curve. So, okay. So, again now we are going to discuss a little bit more in detail about the atomization process. So, atomization processes are excited atoms are there, and then first we have the sample, that is solution here. It comes to the through the nebulizer and oxidizer is mixed, aspirated solution, aerosol solution happens, and then fuel gas and oxidant gas are getting mixed, and then solvent vapor is formed, aerosol or solid gas is formed, and these aerosols can undergo different kinds of chemical reactions which I have already discussed. The formation of difficultly melted oxides, etc., easily oxides. So, all the oxides will form, and then we have the aerosol melt gas molecules, and from the molecules they pick up the electrons, and these electrons will react with the ions to form the molecules. Okay. The molecules will revert to atoms, and from the atoms they can form ions or they can form molecules by combining again, and then there is also possibility that an excited atom is formed by absorbance of the radiation. So, the excited atoms can come back to the ground state by fluorescence or by atomic absorption. In the fluorescence, what we have is another wavelength, radiation is emitted is another wavelength, whereas longer wavelength, whereas in the excited atoms there is no radiation coming out, but the intensity of the transmitted light reduces depending upon the concentration of the sample. Okay. So, this is how the whole thing is organized. In this area there is Burner nebulizer interaction, and here this area completely describes almost all the reactions that take place in the flame. Okay. So, what are the reactions in the flame? We have assuming that we have metal oxide, metal salt MEX. Me refers to metal, X refers to the salt. For example, copper chloride, copper nitrate, or cobalt chloride, cobalt nitrate, cobalt bromide, it can be any salt. Okay. So, in the flame the metal salt will ionize, that is in the solution itself the salt will ionize, and same thing will be carried out into the flame. So, the metal ion will be there, and metal atom and X, that is halogen, where X can be chloride, bromide, etc. Now, this metal will can become an ion by losing an electron, and this metal can combine with another halide ion producing MEY, another salt, that is also possible. So, hydrated chlorides, carbonates, sulfates can form oxides, this is the oxide MEY, upon elimination of HCl, hydrochloric acid. So, what happens to phosphates? Phosphates will form pyrophosphates in the flame. So, temperature of the flame plays an important role in the volatilization of salts, after which the thermal dissociation processes of molecules into the atoms begins. Basically, whenever we enter the sample, temperature temperature of the flame will start all the reactions, but all those reactions are so fast that you may not be able to view them individually. So, this is a phase where non-spectral interferences occur. For example, I had already told you that in the flame there are cyanogen molecules and then CH molecules, etc. Cyanogen, CH, NH molecules, all those things will be present, and this is where molecular absorbance takes place. So, this can cause a little bit of interference, as we have discussed earlier. Apart from that, we have a variety of combustion products such as CO2, carbon dioxide will form because the flame is open to atmosphere, and acetylene is there. So, carbon will be there because acetylene can burn into giving you carbon dioxide. It can also burn to give you carbon monoxide if the concentration of oxygen is less, and then it can get reduced to carbon. Water molecules will be there, oxygen molecules will be there, hydrogen, and then hydrogen ions, atoms, OH molecules or OH radicals, N2, NOx, etc. Here you can see that there are species like carbon, oxygen, H, OH, etc. These are not stoichiometric combinations of the elements, so they cannot be classified as compounds, but in the gaseous state these species have been detected in the gaseous space. So, even though their lifetime could be short, you will see all kinds of spectral evidence in the flame that such compounds are being formed. They need not be stoichiometrically correct, but still they are present for very short time, of course. So, solvent, suppose you extract the sample in a solvent, then solvent also will get into the flame and other possible substances present in the sample also will evaporate. For example, if you want to take determine gold in silver, gold in sea water, then what happens? You want to determine gold, but along with the sample you will have so much of sodium chloride, magnesium chloride and several other elements in the sea water. So, all those things also will evaporate. So, atoms, radicals, ions, etc. are all formed by temperature dependent equilibrium reactions. So, in principle the flame itself can be considered as a solvent. This is very interesting because flame on its own does not give rise to any spectral features. So, it can be considered as a solvent. So, but there are traces of metals could be there in the solvent also. That means, therefore, what we should do is if we are extracting the sample in a solvent, we should aspire the solvent also to obtain the blank reading or reference reading. Okay. So, chemical environment, the temperature and residence time of the chemical species have greatest influence on the concentration of the atoms in the flame. I want you to understand that in the flame the high temperature will be prevalent and then atoms will be there, they are also coming and moving out of the flame, and then therefore, the residence time, how long it remains within the 5 centimeter flame, 5 centimeter length and 3 centimeter height of the flame, how long an atom can stay in the flame in the optical path. So, that will be for a few microseconds maybe. So, all these parameters, flame temperature, residence time and the chemical species whatever it forms, carbon monoxide, carbon dioxide, elemental, all these things have greatest influence on the concentration of the atoms in the flame. So, what happens? Carbon monoxide and hydrogen, they do not have sufficient free energy to reduce metal oxides on their own. That means, if you take a metal oxide, if you take a metal oxide, add a little bit of carbon monoxide, expose it to carbon monoxide or hydrogen atmosphere and then heat the mixture, you may not get the metal oxide reduced to the metal, because the free energy of these carbon or hydrogen radicals are not, they do not have sufficient free energy. There should be, for any chemical reaction, free energy is involved. So, if you read a little bit of thermodynamics, the free energy is the driving force for any chemical reaction, and free energy of the products minus free energy of the reactants gives if it is known, we can predict whether the reaction will proceed on the forward direction or on the backward direction, that is reduction or oxidation. So, that apart, there are C2 and CH radicals are found only in the lower zones of the flame, that means where there are blue flames. Hydrogen radicals remain longer in the flame and hence they play an important part in the production of atoms via thermal dissociation. Okay. So, thermal dissociation itself is a very important pathway for the production of atoms. So, now what we are saying is, ever since I started this class, I have maintained that atomic absorption is a specific phenomena, and there is, if the element is there you get a response, if the element is not there you do not get a response. That means the atomic absorption is essentially free from interferences. This statement is a little misleading, because while 99% of the atomic absorption measurements are interference free, but still we note quite often that there could be some sort of interferences and in the determination. So, what do we mean by interference? What we mean is the absorbance of the sample is lower than what it is, what it should be. If it is lower than what it should be, we call it interference. So, it may be 5%, it may be 10%, or there may not be any signal. So, all these things are possible, but rarely. Now, rarely does not mean not there at all, is not it? Rarely means it will be there, sometimes it will be significant, sometimes it will be, most of the time, majority of the time the interferences will not be there. That means, if the solutions are dilute and there are not many interfering species, the absorbance will be as per your expectation. That we will discuss in the last part of this program. What are the typical concentrations and typical absorbances. Now, I want to spend some time on the interferences in atomic absorption. So, we can see here in this slide that there are different kinds of interferences. Okay. One is spectral interference, and second is transport interference. So, if the resonance lines of two elements are matching and we cannot separate them, then we call it spectral interference. That means, the reading may be higher. And then transport interference, suppose the sample is not getting introduced into the flame properly. So, the number of free atoms will reduce. So, the absorbance will be reducing. Suppose there are more quantity of the sample is being aspirated, more free atoms, that also can give rise to higher absorbance. So, transport interferences are also there, and then solute volatilization interferences. Solute itself may volatilize and go off. So, that is the salt, metal salt, it may volatilize and go off. And then vapor phase interaction, when in the flame, this is another type, is vapor phase. In the flame, everything is in the vapor state. So, there could be interactions in the vapor phase, and the formation of CO, CO2, CH, NO2, NH2, and all kinds of possible vapor phase reactions are possible, and this may cause certain amount of error in the measurement. And then finally, spatial distribution. This is another aspect that is we have already discussed a little bit regarding when we were discussing about the flame height. Typical flame heights for chromium, silver and magnesium I had shown you, and depending upon the spatial distribution of the species, the absorbance could be higher or lower. So, any change in the absorbance value from the expected is called interference. Sometimes interference may be significant, sometimes it may not be. So, these are the different kinds of interferences: spectral, transport, solute volatilization, vapor phase and spatial distribution. We should be aware as chemists and engineers, otherwise we will be reporting wrong results. So, whenever we are talking about atomic absorption, we talk of parts per million, and even if we go wrong in parts per million level, it can be cause significant changes, it may have profound effects if we report wrong results also. So, we will discuss these a little bit further now. So, what are spectral interferences? As I told you, spectral interferences are when the emission wavelength from the primary radiation source or absorption of a concomitant element overlaps with that of the analyte wavelength. That means, two resonance lines, two elements will have same resonance line. So, the monochromator cannot do much, it will measure the total absorbance. Sometimes in presence of higher concentrations of concomitants, substantial line broadening also happens. So, whenever line broadening happens, what happens? Another resonance line of some other element may fall in the broadened resonance line. So, higher absorbance takes place. So, radiation scattering of particles. Here I have written the concomitants means other elements, other compounds present in the sample, but if they are in grams per liter, for example, like in sea water, then substantial line broadening happens and part of the measurement may fall into the resonance line where we are measuring the absorbance of a particular element. So, radiation scattering of particles in the flame or molecular absorption by chemicals and radicals also introduces molecular interference whenever there is resonance line overlap. This I had already explained to you once. That means, in the along with the spectral line, there is a molecular absorbance line which encompasses totally the resonance line. Resonance line is only about 0.002 plus or minus 0.005 nanometers accuracy. But if there is a molecular absorbance which takes fully covers the resonance line, the absorbance at that wavelength adds to the actual interference, actual measurement of the absorbance. So, you get a higher reading corresponding to the contribution of the molecular species at that wavelength, whatever is the concentration. Sometimes molecular absorption can be a source of error, but it can be taken care of. How we will see later. Okay. Whenever there is resonance line overlap, we call it spectral interferences. So, for example, now I am going to give you an example here. Calcium hydroxide, CaOH, not OH twice, calcium hydroxide band in air acetylene flame in the determination of barium. I have a barium solution, I want to determine barium, but suppose there is certain amount of calcium in the sample. So, I as a concomitant, okay, because any sample nobody determines pure solutions, 99% of the time nobody determines pure solutions. So, the aim of analysis itself is to determine a particular element in presence of other elements. Now, I am giving you a situation where barium is to be determined and calcium OH, CaOH is band is there in the air acetylene flame. So, this causes spectral interference because part of the band absorption spectrum of CaOH encompasses the barium resonance line, it totally occupies. Similarly, alkali halides cause spectral interferences below 300 nanometers, whatever is the element you want to determine. If the resonance line is below 300 nanometers, all alkali halides like sodium chloride, sodium bromide, potassium chloride, potassium bromide, all kinds of things will form, will cause error in the determination of iron, and as this kind of interference is especially noted in serum determinations. Okay. So, people want to know how much of sodium is there in the case of blood pressure. No, somebody is having blood pressure, they find out how much sodium is there in the serum. Let us see, doctor will order. So, but sometimes doctor will order determine iron, hemoglobin. What is the hemoglobin in the serum? So, but serum itself will contain lot of sodium chloride. So, this kind of error happens here. So, when the spectral lines overlap or lie outside the resolving capacity of the monochromator, the interference is more serious, because monochromator can differentiate only plus or minus 0.2 nanometer. Okay. But even if you use best monochromator like grating, but if the monochromator is unable to differentiate between two lines, then nothing can be done. There is spectral interference, both of them will add up. This example of vanadium, for example, vanadium, what is the spectral line, resonance line I am showing here? It is 308.211 nanometer. Okay. But what is aluminum? Aluminum is 308.215. So, 0.005, both of them are, if you choose 308.211, 0.005, 216 plus or minus 216, monochromator can differentiate, but this is less than 216. So, any determination of vanadium at 308.211 will cover the absorbance of the radiation line from 308.215, that belongs to aluminum. So, the total absorbance of vanadium will be higher if there is aluminum. So, this is known as spectral interference. That means, whenever spectral interferences are there, what we should see is the spectral line should not be more than should not be more than 0.005 nanometer from the resonance line of the two elements. So, if they are within 0.005 nanometers or something, spectral interference will always be there. So, we have to be careful whenever I have to determine vanadium. First I check whether there is aluminum is there or not. If aluminum is not there, I do not have to worry, but if aluminum is there, I will determine aluminum also and then subtract the absorbance from aluminum from the vanadium absorbance. So, this is how we go about solving the interference problems. And similarly, another example I am giving you is magnesium line of 285.200 nanometer, and what is chromium? Chromium is 0.285.203. The difference is 0.003 nanometer. That means, no amount of diffraction grating or monochromator can separate these two lines. So, there will be spectral interference of magnesium or chromium in presence of each other. If you want to determine magnesium, chromium will interfere. If you want to determine chromium, magnesium will interfere if both of them are there in the sample.